Good morning, everyone. Am I audible?
Morning, ma'am.
And what about the status of the slide? Is it visible to everyone?
Yes, ma'am.
Yeah, ma'am.
Yes, ma'am.
Okay, that means we can start with today's class. And just for the sake of your information, today is going to be the last experiment in the volumetric category. We've already discussed 4 experiments based on volumetric chemistry, and today is going to be the last. And from next term, we'll be starting with the non-volumetric or engineering experiments. Is slide number 2 visible to everyone?
Yes, ma'am.
Yes. So the slide is visible to you. You can very well see that the objective for today's experiment is the determination of the strength of supplied potassium dichromate solution using ferrous ammonium sulfate as an intermediate and potassium pericyanide as an external indicator. Now, the last term in the objective, the last 2 words, external indicator, makes this experiment very much different from the last 4 experiments that you have learned in volumetric chemistry. In this experiment, you will be using an external indicator. External indicator means that we will not be adding it to the contents of the conical flask as you have been doing previously. In this, the indicator will be kept outside the solution, or you can say the reaction mixture, and that will be done with the help of a tile, white tile, and a glass rod, which I'll be showing you right now. So the indicator that will be used, which is potassium pericyanide, this will be placed in the form of droplets on a white tile with the help of a glass rod, and you will be bringing the reaction mixture in contact with it again with a glass rod on the tile, and you will be observing the color change. So the use of an external indicator makes this experiment very much different from the previous ones. Then there is one more term, intermediate, which has been used. You even need to understand what is the meaning of intermediate. This we will be discussing on the coming slides. Ferrous ammonium sulfate solution, this will be used as an intermediate. And if I skip the importance of these 2 terms, then what is the objective? Your objective is to find out the strength of a specific solution which has been supplied to you, and that solution is of potassium dichromate. Does anyone know about the nature of this compound, potassium dichromate? Like, how does it behave as an agent? Is it an oxidizing agent or a reducing agent? In which medium does it work?
Oxidizing.
Yes, somebody is saying something.
Yes, ma'am. Oxidizing.
It is an oxidizing agent.
Oxidizing.
Yes,
Yes,
it is
ma'am.
an
Oxidizing.
oxidizing agent, potassium dichromate solution. Do you know the color of the solution or the salt?
Ma'am, green.
Green?
When it,
No.
when it,
Orange.
red.
Orange. Orange is the color. Yes. And you know it behaves as an oxidizing medium agent in which medium? Which type of medium?
Acidic.
Acidic medium. Yes. So a lot of information about this reagent is known to you. So we can move towards the reaction. That means is slide number 3 visible to everyone?
Yes.
Yes, ma'am.
Okay. So these 3 reactions form the basis, or they are the principle on which this experiment is based, especially the first reaction I'm talking about. This is an ionic reaction. Can you predict each component from where it has been derived? Can you predict from where these ferrous ions are coming from the objective of the experiment, which I have discussed with you right now? From where are these ferrous ions coming? Ferrous ammonium sulfate, yes, which will be used as an intermediate in the experiment. That is the source of the ferrous ions. Then dichromate ions, definitely it is coming from potassium dichromate solution, which will be supplied to you. The unknown dichromate solution will be supplied to you, and your objective is to find the strength of this solution only. And as you have said, this reagent, potassium dichromate, acts as an oxidizing agent in the presence of acidic medium. That is why the H plus ions have been shown in this reaction. And now, if this is an oxidizing agent, potassium dichromate, can you predict the type of reaction which is involved?
Redox.
It is a redox reaction. So if you are telling me it is a redox reaction, you also need to tell me which are the species which are going reduction and which species is undergoing oxidation.
Ma'am, ferrous is
Ferrous
going
is
to
going
oxidize.
to oxidize.
Reduction in iron
Oxygen
oxide.
is
Yes.
reducing.
So yes, you can see Fe2 plus ions when they come in contact with dichromate ions in acidic medium, they are being converted into Fe3 plus ions. So ferrous is being converted into ferric. This is an oxidation reaction. The oxidation number is increasing. So this is the oxidation reaction, oxidation half reaction. What about the reduction part? Which of the specifically which ion is undergoing reduction?
Chromium plus 6 is going into chromium plus.
Plus 6.
Chromium. It is chromium because the oxidation state of chromium in dichromate ions is 6, as you have been telling me, as you have told me right now. So the oxidation state of chromium in dichromate ions, if you will calculate, this will come out to be 6, and it is changing to 3 plus. So that means it is undergoing reduction. So simultaneously oxidation and reduction are taking place, and that is why it is a redox reaction. What about the color? Orange, you have told me that the color of potassium dichromate solution is orange. But what is going to be the color of the resultant solution?
Green.
Yes, green. Because chromium ions Cr3 plus will be formed. So they will impart green color to the solution. The next two reactions that you can see on the slide right now, these reactions are the basis of the reaction with the indicator. The indicator is potassium ferricyanide. The formula for potassium ferricyanide is, be very particular about whether you are writing the formula for the ferricyanide or for the ferrocyanide, because the formula will change in either case. So the indicator that you are using, it is potassium ferricyanide, and it is light yellow in color. The solution of this is light yellow in color. Now, initially, when the reaction mixture will be brought in contact with potassium ferricyanide, it will be containing ferrous ions initially when the reaction has not started. So, ferrous ions, when they will come in contact with the indicator, what will happen? What will happen? These potassium ions will be displaced and ferrous ions will take its place. And the complex that you see, that will remain intact. There will be no change in the formula of the complex. So if Fe2 plus will take the place of potassium, what will happen? Ferroferricyanide. This complex will be formed. Ferroferricyanide. Why ferroferricyanide? Because in the outer sphere, ferrous ions are coming. That is why ferro. And the inner sphere of the complex, that is remaining intact. It was ferricyanide initially, and that will remain the same. So this is ferricyanide. But the valencies, they will be exchanged. This is 3 plus, 3 minus. So that 3 minus will be placed over here. And the charge of ferrous ions, Fe2 plus, this will be translocated over here. So this complex is ferroferricyanide, and it is deep blue in color. So initially you will see a deep blue color. Now when the reaction will proceed, means you will start adding potassium dichromate from the burette into the conical flask containing ferrous ammonium sulfate and acid. The ferrous ions, they will be converted into ferric ions. Now when the ferric ions, they will come in contact with the indicator, which is again potassium ferricyanide. In this case, what will happen? Another complex will be formed, which is going to be ferriferrocyanide. Sorry, ferricyanide. This is going to be ferricyanide. Again, the complex sphere that will remain intact. It was ferricyanide over here, so this will be ferricyanide only. And because you are starting with ferri this time, so this is going to be ferricyanide. And this complex is reddish brown in color. Brown color you will see. So when this color change will be observed, that the color changes from deep blue to brown, that means your endpoint has reached. So this is going to be the observation that you will see. So are the reactions clear to everyone? In fact, if you will follow the manual which is there on the institute's website, just wait, then you will see that only the first reaction has been given and these two reactions have not been given. So please take a screenshot, or you can even copy it down and you can note the reactions for the indicator part. Yes, somebody was asking something.
Ma'am, I have doubt that as we use the indicator as an external, then how it is taking part in reaction, ma'am? Just because put मैम जो हमारा आयरन अमोनियम Fe अमोनियम सल्फेट है मैम, वो तो एक अलग फ्लास्क में है, और मैम जो
Yes,
अपन
so we will. I have not actually discussed the experimental details right now. I was discussing the principle. You will take out a drop of the solution of the conical flask and you will bring it in contact with the drop on the tile. Then you will see the color change. Is it clear?
Okay.
You will immerse a glass rod, and with the help of that glass rod, you will bring out a drop of the contents of the conical flask and you will bring it in contact with the drop on the tile, indicator drop, and then you will see the color. Okay. So this was the principle. Now coming to the procedure of the experiment. Now this will tell us why we are calling ferrous ammonium sulfate as the intermediate. See, ferrous ammonium sulfate solution will be supplied to you and its strength is not known to you, as this has been happening in the previous experiments as well. So if I tell you that the strength of ferrous ammonium sulfate has not been told to you, how do you think you can find out the strength of ferrous ammonium sulfate? As we did it for EDTA. EDTA was not known to us, then what we did in that case? How do we proceed?
known solution of K2Cr2O7 लेना पड़ेगा पहले.
Yes, we have to take a known solution definitely. Then only we'll be able to find out the strength of ferrous ammonium sulfate. So in this case, since the reaction is taking place between potassium dichromate and ferrous ammonium sulfate, that means we have to prepare a known solution of potassium dichromate. So I think by this time you all are familiar with how a known solution is prepared. So very quickly I'll be going through the step. You will be weighing out exactly a specific amount of potassium dichromate crystals, orange crystals, and that amount is 0.6128 gram. And then you will be transferring it to a 250 ml volumetric flask, dissolving it with minimum amount of distilled water at first, and then making it up to the final mark. And for the homogeneous solution, you will stopper the volumetric flask, and you will simply invert once or twice the flask, and a homogeneous solution will be prepared. This I have discussed in detail in the previous classes. Now, once you prepare a known solution of potassium dichromate, then it will be filled in the burette. Potassium dichromate solution will be taken in the burette, and you will be pipetting out 25 ml of FAS solution, ferrous ammonium sulfate, in the conical flask, and to it half test tube of dilute sulfuric acid will be added. This will be supplied. A test tube will be placed near it. You will go and you will simply add half test tube of dilute H2SO4 for the H plus ions. You will add these ions into the conical flask. Then see, a number of drops of freshly prepared solution of potassium ferricyanide will be placed on a clean, dry, white tile by means of the glass rod. This I will show you with the help of a figure. Slide number 5 visible to everyone? Is it visible?
Yes, ma'am.
Yes, ma'am.
Yes, so this is the white tile as you can see on the slide, and with the help of glass rod, you will place the drops of the indicator on the white tile, which will be yellow in color. The drops will be yellow in color. This is a drop of the indicator potassium ferricyanide. Now, if you follow the procedure that is given in the manual, in the first go, they say that after every 1 ml you will add from the burette into the conical flask, you need to check whether the color is changing or not. But suppose the endpoint is lying at say 32, suppose. So that means you will have to check for 32 drops. Are you following what I'm saying? You will be adding 1 ml and then you will be checking. Again 1 ml you will be checking, and if it is lying at 32, 35, so you will have to check for 35 drops. Isn't it?
Yes, ma'am.
So I will suggest what you can do is take intervals of 10 ml in the first go. Or you can even condense it to 5 ml, but 10 ml will be good enough. So take intervals of 10 ml so that you come to know whether the endpoint is lying between 0 to 10 or 11 to 20 or 21 to 30 or 31 to 40 or 41 to 50. This will reduce the number of drops that you will have to use. Got it? So what you will do in the first run of the experiment, in the conical flask, you will take ferrous ammonium sulfate and half test tube of sulfuric acid. Then on the tile, say you will place 10 to 20 droplets of the indicator. Then add 10 ml directly of potassium dichromate into the conical flask, shake the contents, and then dip a clean glass rod into the conical flask and bring out a drop of the solution in contact with the indicator drop already placed on the tile, and see what color are you getting. Initially, it is going to be deep blue color because predominantly ferrous ions will be present in the solution. So see if you are getting color blue or brown. So initially it should be blue. Suppose you get a blue color. What you will do after that, 10 ml you have added, you will check. You get a deep blue color. Then add another 10 ml. Straight away, 11 to 20. 10 ml you have added. Again, take out a drop. Shake the contents, take out a drop and bring it in contact with the indicator on the tile and see what color you are getting. Suppose you are getting blue. Again, then again add 10 ml from the burette into the conical flask, check the contents, check. Now say if you get brown color in the third go. So what will this tell you? If this is happening in the third time, you get a brown color, what will this tell you? About the range of the endpoint, where it can lie. We are checking after every 10 ml. this will tell you that the endpoint is lying between 21 to 30 ml, isn't it? The first time you checked, it was for 0 to 10. Second time you checked, it was for 11 to 20. Third time, if the color is changing, that means it is for 21 to 30. Are you following?
Yes, ma'am.
So that means your endpoint is lying somewhere between 21 and 30 ml, because for 20 it was blue. So that means that was not the endpoint. The endpoint is lying somewhere between 21 and 30. Is this point clear to everyone?
Yes, ma'am.
So, okay. So if you get this, what is the range in which the endpoint is lying? Then after this, what you will do? You will again fill the burette with the known potassium dichromate solution. You will throw the contents of the conical flask, again pipette out 25 ml of ferrous ammonium sulfate and add to it half test tube of dilute sulfuric acid. After that, what you will do? You will straight away add 20 ml from the burette into the conical flask of potassium dichromate. 20 ml added. Now after this, what you will do? You should follow this. Add 1 ml at a time and then check. Means, suppose you are starting from 20 to 21. Add 1 ml and check. Take out a drop and bring it in contact with the indicator on the tile. See, you are getting blue color or brown color. Suppose you get blue. Add another 1 ml from the burette into the conical flask and check. Say again you get blue color. That is for 22 ml. Then third time 23 ml blue color, 24 ml brown color. So what is this telling you? If at 24 ml you get brown and at 23 it was blue, what is it telling you?
Endpoint is 23 to 24.
Endpoint is lying between
23 to 24.
23 and 24.
23 and 24. Yes. So this was the second experimental trial that you did. Now you need to repeat it again for the third time. After this, what you will do again, all the contents you will throw from the conical flask. Again, you will pipette out ferrous ammonium sulfate and half test tube acid will be taken into it. Fill the burette again to the 0th mark, and straight away you will add 23 ml from the burette into the conical flask. Straight away 23 ml without checking. After 23 ml you have added, now you will bring it to an interval of 0.1 ml. Suppose you are adding 0.1 ml, that will be in fact one drop only. So one drop you have added and you will check. Second drop you will add, again you will check. Third drop, and you will see at what drop or at what 0.1 ml the color is changing from brown to blue. And at this stage, when you will see, suppose at 23.3, the color is blue, at 23.4, it is brown. So you will say 23.3 is the endpoint. Is that clear? Because now you cannot enter in between the two. It is at the drop level. This is the minimum precision that you can get with the experiment. So if at 23.3 it is blue and at 23.4 it is brown, you will take 23.3 as the endpoint. Is that clear?
Yes, ma'am.
So this is what are these 2 points telling you on the slide. Same. I have just added one more step. That is the first addition of 10 ml at a time and then getting the idea of the range in which the endpoint is lying. That will actually increase the number of experimental trials by 1, but that will save your time in checking the drops actually on the tile. Otherwise, you can have to check maybe even for 30 to 40 drops. That can be the case. Is it clear? Any doubt in this step or in these 2 steps?
No, ma'am.
So if that is the case, we are done with the experimental part. I'll explain this as well. So this is what I have told you. Suppose the drop gets colored at 20.4 24.4 ml and remains unchanged or brown at 24.5 ml, this implies that the endpoint is at 24.4 ml. And you need to repeat the process for 2 concordant readings as you have been doing in the previous experiment. And this experiment will be repeated for the unknown potassium dichromate solution as well. This experiment will be repeated. Once you will do it with the known solution so that you can find out the strength of the supplied ferrous ammonium sulfate solution. And after that, you need to repeat the procedure with the unknown potassium dichromate solution which will be supplied to you. Coming to the observation part, is it visible? Slide number 7.
No, ma'am. Yes.
Yes,
Yes,
ma'am.
ma'am. Now it is
Yes,
visible.
ma'am.
Now it is visible. Okay, so the first 3 readings that you can see, they are similar to what you have been learning in the previous experiments. First of all, you will weigh the empty weighing tube. Then you will add some crystals of potassium dichromate such that you have to weigh actually 0.628 that was there in the previous slides. So you will add that value to the initial value and you will weigh that much amount, approximately that much amount. Then after transferring the substance, potassium dichromate, into the volumetric class, again you will go for the third reading and say the difference of W2 and W3 give you the exact amount of potassium dichromate that has been transferred or which has been used in making the known solution of potassium dichromate. And how much potassium dichromate will be used for the unknown and known solutions with 25 ml of ferrous ammonium sulfate, that you can derive from the following 2 tables, table 1 and table 2. So please take a screenshot of this slide so that I can move further. I will uploading the content tomorrow. Even for the previous experiments, I will be uploading the content tomorrow. Should I move forward?
Yes, ma'am.
Yes, ma'am.
Then this is table 1 for the known potassium dichromate solution. You will be starting with 0 on the burette. And suppose in the first go, you get to know that the endpoint is lying between 26 and 27. You can make one more column if you are going for 10 ml interval, or you can stick to this format only. It is your choice. So suppose after experimental trial, you come out to know that the volume is lying somewhere between 26 and 27. So then you will check after interval of 0.1 ml and you get the reading as 26.8 as the concordant reading for the known potassium dichromate solution. Again, take a screenshot of this slide. Come to table 2 now. The same procedure will be repeated for the unknown potassium dichromate solution. And again, you have to work for the concordant value. Suppose in this case, it comes out to be 29.2 ml. Again, take a screenshot of this table. Coming to the calculation part, see the final formula I am showing you, 4W, where W is the mass of potassium dichromate for the known solution that has been weighed by you, and V1 and V2 are the 2 values derived from table 1 and table 2. Derivation, I am expecting you to work out. I will not do it for you. Can you tell me the principle on which the derivation will be based? What principle will you apply for deriving this formula? It is volumetric calculation.
law of equivalence लगा है.
Yes, principle of chemical equivalence, that will be applied, and it will be applied between which two substances?
Ferrous ammonium sulfate and K2Cr2O7.
Yes, ferrous ammonium sulfate and potassium dichromate. That is right, because the reaction is taking place between these two substances. So twice it will be applied. Twice it will be applied. Now, as you can see in the formula, V1 is the volume of potassium dichromate and V2 is also the volume of potassium dichromate. And in the final formula that is being used for the calculation, ferrous ammonium sulfate is nowhere. Can you see? Ferrous ammonium sulfate is nowhere. So can you make out now why is it being called the intermediate in the experiment? It is being called the intermediate because it is linking the volume of unknown potassium dichromate solution with the volume of known potassium dichromate solution. It is linking the two. Otherwise, can this happen that the law of chemical equivalence be applied directly between known potassium dichromate solution and unknown potassium dichromate solution? Can that happen? Can you apply law of chemical equivalence between the two? No, that can never happen, because it is not the reaction that is taking place between the two. The reaction is taking place between potassium dichromate and ferrous ammonium sulfate. So since ferrous ammonium sulfate is linking the two volumes together, that is why it is being known as the intermediate for this experiment. Is it clear?
Yes, ma'am. Clear.
So this is the formula that you need to apply, and after this, finally, you will be reporting the result. I think the statement has been given in the lab manual, and please make it in the past tense, that how much you calculated it as. The strength of supplied potassium dichromate solution using ferrous ammonium sulfate solution as intermediate and potassium ferricyanide solution as an external indicator was this much gram per liter. This is how you will report the result. So this was all about the experiment. Now, if you have any doubts in your mind, you can ask it right now. Any doubts you have in your mind? No. If you do not have any doubts, then we can stop over here.